So, to find a complementary solution, so in other words, a function yc that satisfies a constant coefficient homogeneous equation like this one right here, the tactic is very simple. We just look for exponential solutions. So if we had ay double prime plus by prime plus cy equals 0, for example, making the guess that y has the form e to the rx for some r, and substituting it in, we'd get a r squared e to the rx from the double derivative, and then b r e to the rx from the single derivative, and then c e to the rx equals 0. And we can factor out the exponential part. And then we know that if a product of two things is equal to 0, then one of those things has to be 0. And it's not going to be this one because the exponential function is never 0. So from that, we can conclude that it has to be ar squared plus br plus c. That's equal to 0. So now we can go ahead and look for possible values of r that solve the problem will be exactly the roots of this polynomial right here. So this is what we call the characteristic polynomial. And we find solutions to the ODE for the roots r of this polynomial. So in other words, solutions to p of r equals 0. So then there's going to be three cases. We can have it be the case that we find two distinct real roots. So this is the case when PR factors into r minus r1, r minus r2. It can also be the case that we have r1 equals r2, so a repeated root. And so this is polynomial that splits like this. And then the last thing that we can have happen is when we end up with r squared plus r1 squared. So this is an irreducible quadratic. And in this case, there's no real roots. In fact, the roots look like a plus or minus bi, where I is the imaginary number. But anyways, we will see how to deal with all of these situations in the ensuing examples.